Alright, welcome back. In this video, we're over Catalytic Hydration, also known as Hydrogenation, and Syn Addition. I made a lifetime total of $376.80. This video is going to be more of a serious tone. I've had a lot of students ask me, when are we ever going to use these mechanisms in real life? How does this ever pertain to real life, what we're learning? Because you can never see the connection. You are about to see it in this video. This mechanism is so important to your daily life that if you want to live a healthy and normal life without any health problems, you need to know this mechanism, because this mechanism is the reason heart attacks and strokes are happening like crazy, like it's an all-time high in America especially. The reason is because of this mechanism. So we're going to go over it. So here's what we're going to do. I am first going to talk about what is the mechanism, like what's going on. Then we're going to talk about Syn Addition. We're going to talk about the catalyst. Then the big picture. Why is this super important? Then we're going to go over chiral catalysts. And we're going to do some practice problems and then a challenge problem. The next addition reaction we're going to go over is catalytic hydration, a type of hydrogenation reaction. The goal is to use an alkene and add 2 hydrogen atoms to it. This reaction basically turns an alkene to an alkane. So what we're doing is basically a reduction, or this is reducing an alkene to an alkane. So here's what we do. We have our alkene. We're going to use molecular hydrogen gas, or H2. And then we're going to use a metal catalyst. What this will do is basically add 2 hydrogen atoms in exchange for using the pi bond. So all we basically do is just remove the double bond. That's all we're doing. We don't need to draw in the hydrogens really, unless it's chiral. If it's not chiral, you don't need to do anything because you don't draw in hydrogens. So all you're really doing is removing the double bond. There is no mechanism that I'm going to show you. The reason is because this reaction cannot be shown through Lewis configuration, I should say, or Lewis drawings. All the reactions we've been doing have been using Lewis structures. We're dictating, where are the electrons and where they're going. Those are basically Lewis structures. For this, it's impossible. The reason is because what's really happening in this mechanism is hydrogen gas, or molecular hydrogen gas, is interacting with a metal, but not really using its electrons. And what happens is the bonds break between H2 and then get added to the alkene. So it's very complicated and it's too advanced for organic chemistry 1. Even organic chemistry 2 is a little too advanced. And it's there's really no good way to show it. So we don't really learn the mechanism. There's no reason to. All right, Syn addition. Just like hydroboration oxidation, if 2 chiral centers are created, the hydrogens must be installed on the same face. Both must be on wedges, and then both must be on dashes. So here we have our alkene. We do the reaction, and you'll notice that this is an ethyl group gets installed on a wedge, and this methyl group gets installed on a wedge. The hydrogens are not shown because you do not need to draw the hydrogens. In reality, the hydrogens are on dashes here, and that's Syn addition. The reason we're putting wedges here is because the molecule is chiral, so we need to show both wedges and dashes. But since we're putting the hydrogens on dashes here, we don't need to draw in the hydrogen. There's no need to. But what we need to draw in is the wedges for the other functional groups attached. Same goes for here. What we're doing is we're drawing the dashes are going for the other functional groups that were on the molecule. But for hydrogens, which we are attaching through Syn addition, both of them are on wedges, but there's no reason to draw in the hydrogens because you don't draw in hydrogens. But in reality, they're actually there on wedges. We just don't draw them in. You just need to draw the other groups on the opposite configuration. Hopefully that makes some sense. Oh, one thing I forgot to mention for hydroboration oxidation, and this, is if you create two chiral centers, but that physical molecule is symmetrical, it's meso, meaning you only get one enantiomer. And we're going to do an example problem. I purposely added a practice problem here for you guys to show what would happen. So if you don't understand what I just said, you will when you do the practice problems. So with the catalyst. Okay, in reality, the metal catalyst is not needed. It just lowers the activation energy so the reaction can proceed faster. But really, yeah, like I said, it doesn't need the catalyst because catalysts just lower activation energy so the reaction can happen faster and easier. The reaction could happen, but it would take an eternity. You would basically never see the reaction happen. But legally saying, like, we had to say that, it still can perform, like the reaction still can go through without the catalyst, but it'll take so long that we really wouldn't see it. So that's why we add the catalyst. We can use 3 different types of metal catalysts. We can use platinum, we can use palladium, or we can use nickel. These are all fair games for exams. You could see either of these 3, but it's going to do this. It's going to do the same thing. The mechanism is all the same thing. Okay. The big reason why everyone needs to know this concept, and I'm going to open your eyes right now. Triglyceride is basically fats and oils in our natural world. This is an unsaturated fat. You will notice that it has double bonds. Unsaturated fats have a low melting point. Unsaturated fats, a good example is like vegetable oil. Vegetable oil is an unsaturated fat. But the problem with unsaturated fats is they can go bad easily. They spoil fast. So what we can do is we can use catalytic hydrogenation or hydration, the mechanism we just went over. And what this does, it removes all the double bonds. It removes these. And it turns it into a saturated fat. But there's a gigantic consequence. Catalytic hydration is not a perfect mechanism. Sometimes it does not remove all the double bonds. Here's what happens. You do the reaction. You put unsaturated fat in a beaker and you put your ingredients, hydrogen, molecular hydrogen, and your catalyst. What will happen is it will indeed remove all the double bonds, but there is a chance that one of the double bonds can go back to the molecule, but it will be installed in the trans position. This is also known as trans fats. The reason people do this and why companies do this and why it's a very common in America is because this increases shelf life. I'll give you a very good example. Butter. Butter is not supposed to be solid or partially solid. It's in real life, butter is not supposed to do that. You go buy butter, for example, Land of Lakes or whatever butter you like. You go buy it from the store and you open it up. It's partially solid. Especially if we put it in the fridge, it's basically solidified. That is not normal. The reason it solidifies is because of this reaction we just learned, catalytic hydration. Because what happens is when you move the double bonds, this molecule becomes more rigid. And you're probably wondering that's a little counterintuitive because you would think that double bonds create the rigidity because they're not, they're not flexible. I can see that logic, but what really happens is these bonds get compacted together. Because they're so flexible, they get compacted together and they kind of solidify. They become very rigid and solid. That is why butter is semi-solid. This is exactly why. but there is a consequence. This is not a perfect reaction. Therefore, sometimes you get trans fats. This is why on the butter container, you will see trans fats in there. It's going to be like 0.5 grams, but it's there. And this is what's really bad for you. And I'm going to tell you why right now. When you consume trans fats, it goes in your body, right, and gets absorbed. Your liver is going to produce something called very low density lipoproteins. What this is basically a vesicle to transport cholesterol and other fats around the body. Because let's think about this. Why do we need cholesterol throughout our body? It is necessary. Well, one reason is cell membranes. Your cell membranes are made up of cholesterol and like phospholipids and stuff like that. But how do we transport these kind of stuff? When we consume something, how do we get it to the cells, to our periphery? Through very low density lipoproteins. So what happens is when you consume trans fats, your liver is like, uh-oh, we have an influx of this and we need to get rid of it. We don't like it. We need to get rid of it. So it packages cholesterol and stuff like that into very low density lipoproteins and ships it out. Once it gets shipped out and in your circulation, it transforms into low density lipoproteins. But what happens is when you have too many LDLs, low density lipoproteins, and the reason you would have more is because trans fats upregulate the production of VLDL, very low density lipoproteins. It upregulates it. Well, if it upregulates very low density lipoproteins, it's going to upregulate low density lipoproteins because it's the same thing. It just gets transformed. It's just this form is when it's in their blood circulation. So it's going to be the same, same amount. But when you have too much LDLs, low density lipoprotein, it gets stuck in your arteries. What happens, it actually kind of slips under the walls of the arteries and it gets stuck there. Well, what happens then? Well, macrophages will come and eat it up. But when that happens, it creates this plaque residue in your arteries. And that is why people get heart attacks. Exactly this reason. That's why trans fats are so bad. It's because trans fats upregulate all this kind of stuff and then they get stuck in your arteries. Because remember, arteries go away from the heart. They go out to our cells in the periphery. That's why they get stuck. HDL sends it back to the liver to get cleaned. That's a good thing. So it sends back cholesterol we don't need to the liver to be cleaned. But the problem with trans fats is it downregulates the amount of HDL produced. Remember, HDL is like high density lipoprotein. It's same thing as a very low density, but it's called high density and brings it back to the liver. That's our good fats that we like. Even though they're kind of like the vesicles, the transport mechanisms, but that's the good stuff. That's what we like because we like the bad stuff to go to the liver to get cleaned out. But when you consume trans fats, it downregulates the production of these vesicles or these transport proteins. And that's why it's super bad. I'll give you a very good example of why people do this, fast food. McDonald's used to do this. The reason is because they want to save money. Vegetable oil goes bad very easily. The reason it does is because oxygen in the air will interact with these double bonds. When it interacts with these double bonds, it turns into a peroxide. And it basically it turns rotten. The oil becomes bad. So that is why we use catalytic hydration to get rid of those double bonds so oxygen can't react. But in turn, it turns the oil harder or more dense. That is why. And You're probably wondering, this partially hydrogenated, the reason it's called partially hydrogenated is because only partially of its got hydrolyzed, or hydrogenation, only part of it lost its, the double bond. Here it still exists, that's why it's partially. Hopefully this was eye-opening and now you understand what's going on. And hopefully you paid attention, because this what I just explained has to do with the challenge problem. And the reason I made a whole song and dance about it is because your professor may bring this exact problem up to you on the exam. He may give you this and may give you this and say, solve it. Give me the reactants, or the what you need to put in the beaker. That's why. Okay, let's talk about chiral catalysts. This is also very important. And this will also be eye-opening. This video is a lot of information. I'm telling you, it's a very good video. Okay. Now, what happens if you do not want both enantiomers? You just want one of them. Because remember, in Syn Addition, we're making both of them. What happens if you just wanted this one? Or you just wanted this one? Well, smart people realize that you can use a catalyst that's actually chiral. We won't go over it, just know the catalyst is chiral. This is very, very important in synthesizing drugs. I'm going to give you a very good example right here. These two molecules are precursors of L-DOPA. L-DOPA is a precursor to dopamine. People with Parkinson's have problems with dopamine. They don't have enough dopamine. So they realize that they can synthesize L-DOPA and give it to them to help them with Parkinson's. Here's the thing though, the big problem. Only the S configuration of L-DOPA is safe. The R configuration of L-DOPA is toxic, it can kill you. That is why we use a chiral catalyst here, to get the S configuration. If we just use, platinum, palladium, or nickel and did this reaction, you would get both enantiomers, and if you were to administer that to somebody, they would die. That's why. I'll give you another very good example. Adderall. Adderall is made up of the left-hand version of amphetamine and the right-hand version of amphetamine. Dextroamphetamine and is it levoamphetamine or levodextro, whatever. Left and right. One half corresponds with increased cognitive function. The other half, the other enantiomer, corresponds with higher heart rate. Now imagine this. If you were to give one, say if you gave the hand that gave higher heart rate and you gave too much of that, you could kill somebody because they would get a heart attack. So that's why they have the ratios is more cognitive, and the less of the heart part, the higher heart rate. That's why it's super important. And so if you were to see something like this and you get, you're removing a double bond, and then you get, one, the S or R on an exam, you're using the chiral catalyst here. Oh, you know what? I forgot to put the I forgot to put the double one here. Okay, there. Sorry. Okay, good. Let's do some practice problems here. Tell me the product of the following catalytic hydration reactions. Okay, so look how easy it is. Remove the double bond. We put the hydrogen here, and we put the hydrogen here. They are both chiral. These two carbons are both chiral. So it's going to undergo Syn Addition. However, it's meso. Because when you remove the double bond, they're symmetrical. if I were to draw the dash configuration, right, so this one and then the dash one, it's exactly the same molecule. That's why. So you have to be careful. Let me add it back. Ooh, there we go. Okay. Let's do this one. Okay, remove the double bond. Hydrogen goes here, hydrogen goes here. Well, this is CH2, so it cannot be chiral. This one is chiral because it has 1, 2, 3 different branches plus the hydrogen, which makes it chiral. So we only worry about putting wedges and dashes on this one. And so the methyl group gets put on the wedge, and an invisible hydrogen, which we added, is on a dash. And in this one, the methyl group is on a dash, and the hydrogen is on a wedge. In reality, yes, Syn addition is happening in the background. We just don't see it because there's no reason to write wedges and dashes if it's chiral. Let me tell you why. So look, okay, I'm gonna draw in the hydrogen here on the dash. I'm also gonna draw the hydrogen here on a dash because it's Syn addition. They must be on the same face. So both must be on dashes or both must be on wedges. That also means that there's a wedge here. That's ugly, sorry. There's a wedge here on hydrogen. But there's no reason to draw both hydrogens. You could. You wouldn't be, you wouldn't be wrong. You could do that. But in organic chemistry, we just don't write hydrogens. So that's why we don't include it. But in reality, yes, it is Syn addition. They are being added on the same face. Syn addition always happens no matter what. The definition of what's the hydrogenation mechanisms are Syn addition. That's by definition. It's always happening. The hydrogens are always added on the same face. They must always be on both on wedges, or they must all be on dashes. Doesn't matter if it's chiral or not. What matters is when it's chiral is if we draw it in on our paper, on our physical exam. Are we drawing it in or not? Since it's not chiral, there's no reason to draw it in, but in reality, it is being added on the same face. But the big picture is when it's chiral, then you draw it in. Then you must draw in wedges and dashes. But if the carbon is not chiral, there's no reason to draw it in. That's the big idea about it. Hopefully that makes sense to you. If it doesn't make sense, just let me know in the comments and I'll explain it better. Okay, the challenge products. Tell me the products of this reaction. I'm not thinking. Okay, we had this super complicated molecule here, and we do this reaction, hydrogenation reaction. What do we do? There's a reason I told you to pay attention to this. Because hydrogenation reactions remove all double bonds, even though this is a exception here, but that's just too advanced. But they remove all double bonds. So these two double bonds are going to get eliminated and replaced with two hydrogens on each alkene. Well, here's the thing. Okay, think about this. Think about it very carefully. How would you answer this? Well, these must be added as Syn addition. These must be added on Syn addition. So we could have these hydrogens on wedges and these hydrogens on wedges. We could have these hydrogens on wedges and these on dashes. We could have these on dashes and these on wedges. Or we could have these on dashes and these on dashes. I know it's crazy. Here's the answer. Look at that. Isn't that just terrible? Yes, so you have to think about every single configuration when doing these problems. This is a very good challenge problem for an exam. It's seeing if you're paying attention. So like I said, all the hydrogens could be, on dashes. Syn addition here and Syn addition here. You got to think about them separately. So think of these as separate reactions. I could have Syn addition of wedges here, and I could have Syn addition of dashes here. I could have Syn addition on wedges here and Syn addition on wedges here. Or I could have Syn addition on dashes here and Syn addition on wedges here. Now, the other groups must be forced onto whatever is not on the hydrogen. So these are in dashes. This forces the methyl group to be on a wedge. It doesn't have an option. It must be on a wedge. That being said, if you put the hydrogens on wedges, the methyl group must be forced onto a dash because it's not part of the carbon skeleton. Since it's not part of the carbon skeleton, it must be either on a wedge or a dash, and it depends what you're putting your hydrogens on. Same goes for this methyl group. Whatever this methyl group is must be opposite on what you're adding to your hydrogens here. So if you're putting these hydrogens on wedges, then this methyl group must be on a dash. If you're putting these hydrogens on dashes, this methyl group must be on a wedge. Hopefully this makes sense. Just think about it as, separate hydrogenation reactions and then combine them together. All right, if you found this video helpful, please like and subscribe. Until next time, later.